Yep, let's start.
Okay. Hi, everyone. It's good to see who's here. Again, you can stay Zainab or you can change your name. I want to welcome everyone to the first Brain Stimulation Journal Club. I want to thank all the speakers for agreeing to speak here today. Zainab is moderating and organizing it. And in a moment, you'll hear from Mark George, who's the editor-in-chief. I want to say that our goal here is to showcase the best science across neuromodulation. I know that when Mark George, who's the editor-in-chief and co-founder of the journal, recruited me to help, I asked him what really are the goals of the journal, and he basically said one sentence. He's like, to promote the best science across brain stimulation. So that's exactly what we're going to do with this journal club. I'm hoping that we can keep the culture informal, encourage discussion, of course, and also keep things respectful. And so thank you all for being here. And so I wanted to just please have Mark George say a few words, since we're here because of him. Mark.
Hi, thanks for letting me join in, and thanks for doing this. So yeah, I just want to echo Marom and say I'm extremely excited about this initiative. So when we started the journal over 14 years ago, people didn't know about brain stimulation. I knew that this field was going to have legs and really take off, and we wanted a forum that would promote the best science, and it has been that. But I've always struggled because the journal itself is kind of two-dimensional. It's flat. There's dialogue between the authors and then the reviewers, and there's some give and take, and then there's a finished product, the paper that's posted. And there's relatively little digestion or active kind of discussion, or it's not living. It's kind of a dead document sitting there. And I've always wanted ways to make the journal kind of come alive and promote lateral discourse. And so when Marom mentioned this, I said, oh my, maybe that's the answer. And so I'm really excited about this. I've even got another dream, and maybe at a different time you could talk about this, but the journal is now totally free. So you can go, and it's all online. There is no printed journal anymore. So it's all online there. And wouldn't it be wonderful if you all were to do this and then to agree to have the taped journal club just sitting next to the actual printed journal. And then people could click on that. So you could read the journal. And then if you're wondering what people think about it, you could just at any time, at any place on the planet, listen to the journal club. So I'll put that out there. If this is exciting and people like it, maybe we can talk with Elsevier about actually using this as a mechanism to do my long-term goal of bringing these manuscripts alive. And that would be kind of fun to look back, 3 or 4 years from now and say, what did people think when it first came out? Oh, they didn't know that this next thing was going to happen. So it'd be a wonderful way to document the history of the evolution of thought. But anyway, I'll stop now and let you guys take off. But let me know if anybody's interested in actually making this more kind of formal. The people who present could actually get credit on a CV, for, yeah, I presented at this journal club and there it is. It's they would be the equivalent of a letter to the editor or something, I think. But anyway, thanks so much. Good luck. Bye.
Thank you so much, Dr. George. And thank you, Marom, for all the opening remarks. And yes, from now on, Brain Stimulation will be having a monthly, at least, journal club to discuss the recently published papers on important topics, which is really hard to choose across all of them. And this month, every journal club will be on a theme. And this month's theme will be individualized non-invasive brain stimulation, which is highly important, knowing that tDCS lacks method to individualize a stimulation dose compared to other brain stimulation methods. And let's point out some housekeeping notes before starting it. All of the people are muted upon the entrance. Please keep yourself muted throughout the whole talk. You can type in your questions in the chat section throughout the whole session, and I can convey them to the speakers at the end of the talk or at the end of the session on the Q&A section. And also, if you wish to ask your questions yourself, you can unmute yourself at the end of the talk if you want to. And yes, without further ado, let's dive into the topics today that I'm really excited about. And our first speaker is Dr. Caryas Evans from University College of London. So Dr. Evans, floor is yours.
Hi, thank you very much. I will just attempt to share my screen to start with. While I'm doing that, I'm just firstly really grateful to be here and really excited to talk about this. I think it's such a nice idea to get us all together and really get dialogue flowing, because we read all of each other's papers, but to sit around and talk about it is quite a nice luxury. So thank you. You should all be able to see my screen now. Can you see the presentation? Fabulous.
Yes, we can see that. Perfect.
Excellent. So yes, I'm going to talk to you about how one might reduce E-field variability with dose-controlled stimulation. So as I'm sure most of you are aware, when we typically apply electrical stimulation, or tDCS as most often used, we apply a weak current between two electrodes, an anode and a cathode. And we do this in order to try and modulate cortical excitability. But for anyone who has experience using these techniques, is very aware that the physiological or behavioral outcomes are highly variable. For every significant effect that we see with stimulation, another study might produce null effects or non-significant effects of stimulation. So naturally, the thinking now is that this one-size-fits-all approach that we have been administering may be contributing to these variable outcomes. And what I mean by that is applying a fixed dose of stimulation, such as 1 milliamp, and a fixed electrode montage. Luckily, due to the improved sophistication and accessibility of current flow models, we can really start to peel back what we're doing when we apply current to sort of analyze these variances and even try and reduce them. So in terms of trying to quantify current in the brain using these models, I think there are three principal components to maybe trying to improve TES effects. One is intensity, which is what we predominantly or often talk about, which is trying to maximize the intensities of electric field in our target site, so the cortical target in the brain. Also focality, trying to do that whilst also minimize the amount of current that is received in non-target regions, but notably doing that can come at the cost of intensity to an extent. And then a third point that is not as often talked about, but still equally important, is trying to appreciate the direction that current is flowing in the brain. So in our cortical target, trying to ensure that current is flowing in a way that optimally stimulates the neurons we're trying to target. So today I want to talk about mostly the paper that was published in the Brain Stimulation Journal, looking at how to assess and reduce variability in intensity, but time permitting, I might touch upon some preliminary data we have that's quantifying this variability in direction as well. So the general idea, as I mentioned, is with intensity, we want to try and maximize the electric field in the target region that we are stimulating. However, in trying to do that, the question mark remains of how variable that intensity might be in our cortical target. So what we try to appreciate firstly is what this variability looks like. So when you apply a fixed dose of stimulation, such as 1 milliamp to the brain, what might we expect to see inside, so in the cortex itself? Anatomical variances such as skull density, skull and CSF thickness, and all these different individual differences means it's very likely that the intensities we observe in the brain and in our cortical target may be very, very different with this fixed dose approach. So we wanted to quantify that as a first point. But then we wanted to see whether with a very simple protocol, you could effectively eliminate that variability. So rather than applying a fixed dose of stimulation to the individual, can we apply simply increase or decrease the stimulator output to fix the intensities we record in our cortical target? So effectively shifting the variance from inside the brain to the stimulator output instead. So the way we assess this is with current flow modeling, and we use the modeling technique ROAST, which is conducted through MATLAB. And we assess the current flow models in 50 structural MRIs taken from the Human Connectome project that were with the electrode montage designed to target left M1. We first modeled a fixed dose across these 50 subjects of 1 milliamp and 2 milliamps of stimulation, because they are the typical intensities we observe in the research field. And on the basis of those models, we extracted through data processing methods the intensities we observed in the left M1 in each individual. So we did that by creating an ROI sphere of 5 millimeter radius in left M1 and extracted the electric field from that area. On that basis, we then used a simple equation to adjust the stimulator output, reran the analyses to see if we could effectively fix the intensity in that region. So just to describe the actual data that we observed, so here we have plotted the intensities observed in the left M1 ROI when applying 1 milliamp and 2 milliamps. And what we can appreciate is that the variance in electric field is high. So for 1 milliamp, we have anywhere between 0.1 to 0.3 volts per meter observed in our ROI. And for 2 milliamps, we have anywhere between 0.2 and 0.6 volts per meter. So very variable. So what we did is we then took the average intensity we observed across the sample, and we decided to fix the intensity at that. So in this case, it was 0.185 volts per meter as the average for 1 milliamp. And for the average of 2 milliamps, it was 0.369. So by using a simple equation, we effectively demonstrated that you can eliminate this variability. So simply adjusting the stimulator output, either increasing stimulation or decreasing, you could shrink this variability down. Instead, the variability shifted to the stimulator output itself. So we see the same sort of ranges of variance now, instead of being within the cortex, is now with the stimulator output. So to receive 0.185 volts per meter, we were using anywhere between 0.5 milliamps to 1.5. And for 0.369, anywhere between 1 and 3 milliamps. So we've effectively shifted that variance as we expected. We also wanted to appreciate how much this could be a problem in smaller sample sizes. So what we did is we actually conducted some bootstrapping analyses with this sample data to recreate different populations of individuals to demonstrate how smaller sample sizes might have very different electric fields within the brain when you apply a fixed dose. I'm going to focus in on the red distribution and purple distribution curves here, because they're a sample size of about 15, which still can be seen in brain stimulation literature. And what you can appreciate is in this red sample, the average intensities are much lower with a fixed dose compared to this purple sample here, where the average intensities are a lot higher in the ROI. What you might expect is potentially different outcomes in these populations, which might feed into this problem that we're having with replication or seeing recurrent effects with the same sort of protocol applied in different groups. You might suppose that this population would have significant effects of stimulation and this population might not. But it really just shows how smaller sample sizes exacerbate this issue of variance when applying a fixed dose. Just expanding outside of our region of interest, we also looked at the spatial distribution of electric field across our population. And what we can again appreciate, and these are with, on the left here is 2 example participants that were our more extreme examples, is that when you apply a fixed dose, we have intensities above 0.1 volts per meter in this individual here, participant 41, expanding to far fewer areas of the brain. Whereas this participant 14 has much greater spread of electric field above that boundary. Whereas when you apply a dose-controlled methodology, we can see that their distribution above that threshold are much more similar. Likewise, when you look at the entire population of this sample, you can see that when you apply an individual dose, this white area denotes areas where 100% of the sample received over 0.14 volts per meter. And we can see that this is a far greater area than the fixed dose distribution, again, indicating that we've sort of led to more consistent distribution of electric fields over a certain threshold with a dose control method. And so what this really is sort of demonstrating is that not only do we want to maximize the electric field, but we really want to fix the electric field in this target. So by doing that, we might be able to minimize the variability in the outcomes we observe, because not only assessing that in the target, but appreciating what it might mean for the neighboring networks receiving high intensities of current, you might expect variable outcomes. Now, briefly, because I don't want to take up too much time, I just want to touch on some of the directional data that we've also been looking at. And this is just trying to quantify the variability in current flow direction in a cortical target as well. So generally, we understand that direction of current matters. And what I mean by that is that the direction in which current is flowing through a cortical target can lead to different outcomes of stimulation. We typically utilize this idea by either placing an anode or a cathode over our target, with the idea that loosely this will either increase or decrease excitability respectively. The reason we understand that to be important is because of the direction that current is flowing in each neuron. So when you apply current to the surface of the brain, using the surface as a proxy for the orientation of the neurons within it, if current is flowing inward, current may be flowing from dendrite to soma, causing somatic depolarization, whereas current flowing outward may cause somatic hyperpolarization with the opposite effect on the dendrites, and current flowing tangentially may lead to no polarization effect or very little effect. This was explored by Rorji and colleagues in this well-known paper, where they explored the effect of different montages of electrical stimulation on MEP size. And what they found is that when you apply electrodes perpendicular on either side of M1, current was more uniform and had more radial inward current in this M1 bank, and that led to significant effects of stimulation on the MEP size. Whereas a medial lateral montage, where current flows along the gyrus itself, led to less uniform and more tangential current. So again, just quickly, we wanted to explore, again, in a large sample of MRIs, what current flow direction looks like and how variable this is across these three montages. So we looked at the PA montage, the medial lateral montage, similar to the Rorji and colleagues, but also the conventional montage where you apply one electrode over the region of interest, in this case, the anode, and the cathode over the contralateral forehead. We then extracted the direction of current in 4 regions of interest, 2 over our target region, M1, in the crown and in the bank, and also in a functionally relevant but adjacent S1, the primary somatosensory cortex, in the bank and the crown. Now, I don't want to spend too long because I know we've got many other talks to get to, but briefly what I wanted to demonstrate is, firstly, we can appreciate that the distribution is very different, the current direction across each montage, where red denotes radial inward current, blue denotes radial outward, and green is tangential. But we can appreciate in these ROI maps here that with a PA montage, we seem to be getting quite uniform radial inward direction in our M1 bank, and more tangential or less uniform in the M1 crown. Notably, we get radial outward in the adjacent S1 bank. And we see that, again, Rorji might have shown positive effects of this protocol because we have this nice uniform effect on the bank. Medial lateral shows predominantly tangential across all those regions of interest, which again, might support the fact that this might not yield significant effects across a population. Whereas conventional, we actually see the opposite, where it's the M1 crown that is getting most of the radial inward current at the top here, and more tangential in the bank. So what this suggests is, whilst the PA and conventional montages might both yield positive effects or significant effects of stimulation on physiology, the mechanisms by which that occurs could be different. But most importantly and critically for this talk, and this is again looking across the sample, we can appreciate, if 0 denotes radial inward current, that some individuals are getting this, but some individuals are getting more tangential current in these regions. So we can appreciate that that variance is still very much present. So if this is the M1 bank with the PA montage, while some may have the current that we are trying to achieve, some may not. And the similar issue occurs in the M1 crown with conventional montage as well. So just sort of bringing it all together. So critically, what we determined is that you can very simply fix the electric field intensity as one point of reducing variability by simply adjusting the stimulator output. But we also could appreciate that the variability in direction is maintained, and this, as is becoming more of a thought, inviting the need for individualized montages as well. So we haven't explored that bit at this stage with our data, but it kind of points to this idea that we really want to appreciate that anatomy and adjust the electrodes accordingly. Thank you.
Thank you, Dr. Evans. Okay, so let me ask a couple of questions, because for the interest of time, we can get back to it at the end. I guess Miles is asking, do you know if or how the induced electric field at a fixed intensity differs for electrode distance? For example, if cathode and anode are more distant from each other, does this induce larger variability than the electrodes are closer to each other?
I haven't explored several different electrode combinations. We did look at the sort of, so in this example that I pointed out, we actually used that PA montage for the dose control as our primary electrode montage, but we also simulated the conventional montage where you place an anode over the cortical target. We found the variability to be fairly consistent across the two. So I do think, in terms of distance between electrodes, I imagine that the variability would be quite similar, but you would add another component, which is what that focality is doing to shunting, which may add a level of complexity. So if, for example, you have electrodes very close together, you might lose some of that intensity due to current shunting across the scalp. And this could lead to another element of variability in that as well. Depending on the individual anatomy, how close, if you're going for example, standard coordinates, how close these electrodes are to each other on a smaller head to a larger head, you might add that next layer. So we didn't look at it specifically, but I imagine that could be pose another problem.
And another question is about the electrode size, and the same thing. So does the electrode size play a role in that or not?
I think for the reasons I just described, it would probably be a similar issue. So we know that, with larger electrode sizes, you could, if they are closer together, have the same shunting issue, I would imagine. So we have the same issues come into play, which is why I think, it's quite important to appreciate all these elements. If you're going to use, for example, a standard coordinate system like the EEG 1010 coordinate system, what that might mean to the distance between electrodes on a smaller head to a larger head, this could be another issue.
Great. So one more question, and then we will, for the interest of time, we go to the next speaker. This question is, What about the DTI data? Do you think for direction of electric field, DTI images would be important for better individualization of the stimulation?
I think for specificity, the more detailed we can get, the more accurate these models can be. So, for example, with the current ROAST modeling software, it breaks everything down into even just 6 tissues. So we appreciate skull, scalp, CSF, and so on. But we don't go into the more fine-grained tissues. One thing I noticed can be problematic is the way it segments dura can be regarded as gray matter, and that can affect the estimation. So likewise, I think anything for DTI being an extension of that, anything that is more detailed could appreciate where this current is being drawn and where it's flowing. So yes, in an ideal world.
Yeah, thank you so much.
No problem.
Okay, well, our next speaker will be Dr. Aprinda Indahalastari, and she'll be talking about individualized tDCS modeling and in functional connectivity in older adults. So, Dr. Indahalastari, the floor is yours. Go ahead.
Thank you, Zainab. I'm attempting to share my screen as quick as possible, and I think I made some mistake. All right. Is showing the right side of the presentation?
Yes, it is.
Okay, perfect. Good morning, everyone, or good afternoon, evening, depending on where you are. I'm very excited to be here. Thank you for inviting me to this journal club. And today I'll be talking about one of our paper entitled Individualized tDCS Modeling Predicts Functional Connectivity Changes Within Working Memory Network in Older Adults. It's a very long title. Okay, just a brief outline here from my presentation following organization of the paper. We'll start with some background and then moving on to methods, results, and finally close with summary. Okay, so let's start with working memory and aging. So shifting the gear a little bit here from young adult to older adult population. So as we age, unfortunately, our brain starts to decline. So this is true for structural or anatomical or as well as functional decline. And particularly the prefrontal cortex, which shown in the image here, exhibits a strong age-related changes. And this can affect cognition, such as working memory. And working memory is important and critical for decision-making. And this can cause loss of independence in older adults and therefore can affect their quality of life. So the bottom right here showing a graph of relationship between working memory performance and age by decade. And we can see here that there's a sharp decline between decades 70s to 80s. So therefore, there is a need to find an effective intervention method to improve working memory performance in older adults. So some of this might be a review. So what is tDCS? Most of us probably know what it stands for. It's Transcranial direct current stimulation. It's a type of non-invasive brain stimulation that can modulate brain function, whether it's motor function or cognitive function. So for this paper, we're focusing on cognitive function. And we apply a weak constant current in tDCS, in this context, 2 milliamp. And to put things in context, our smartphone needs about 2 amp to charge. So that's 2000 milliamps. So the amount of current is pretty mild here comparatively. And how can we apply the current? We use electrodes. So this paper, we use conventional tDCS. So we use a larger type of electrodes, which is 5x5 carbon pad here that is inserted into this 5x7 centimeter sponges. So which is this pink and blue rectangular here. We wet the sponges with saline solution because we place this electrode directly on the scalp. We want to make sure that the current can flow from electrodes to the scalp, eventually to inside the head. So where should we place this electrode? We use the 1020 EEG system electrode placement as shown in the bottom right here. So for the context of the paper, we place the electrode at F3 and F4 location. So F4 is this red or pink sponges here, and the F3 location is the blue sponge here. So the prior study from our research group looking at relationship between tDCS and functional connectivity in older adults. So this was a mechanistic study that applied acute in-scanner bilateral tDCS, about 2 milliamp for 12 minutes during an N-back task, specifically called a 2-back task. It's a working memory task. And this study found increased connectivity within the working memory network, specifically between the left dorsolateral PFC, that's prefrontal cortex, or DLPFC, and left ventrolateral PFC, or VLPFC, as shown in the image on the right side here. So the sphere that is closer towards the front of the brain is DLPFC, and VLPFC is the one that's closer to the middle of the brain. The increased connectivity that was found in the studies was only true for the active stimulation and not sham stimulation. And it's for the contrast during over baseline. So that means it's during stimulation compared to before or pre-stimulation. So some challenges in tDCS, this might be a theme for today. We know that although tDCS have shown some benefit in functional and behavioral outcome, improving brain function, the exact mechanisms are still unknown, right? So we assume that the electrical current delivered from tDCS from the scalp, eventually reaching the brain, can modulate the membrane potential surrounding the neuron, make it more or less excitable. But the challenge here is that it is difficult to directly measure this electrical current being delivered to the brain in vivo. Therefore, we use computational models to help us guide to see what the current looks like inside the brain. So this is just cross-sectional view of the brain on the top to show that the current density, which is, or J, which is the metric to measure current per area, goes everywhere in the brain, right? It's not only focusing on one single region. If we plot this current density in the surface of the cortex, in the context of where the electrode is placing, in this case F3, F4, we see that the large sum of current is actually accumulating in between the electrode rather than directly underneath them. So right now, tDCS is widely applied as one-size-fits-all application, which carries a touch base before. So if we take a look at this 3 different MR images from 3 different people, we see that there is a variation in terms of head shape, brain shapes, and ventricle size, and so on. So the question becomes whether this one-size-fits-all application is good enough given that we have this individual anatomical differences among us. So this is just an example of 3 different head models with F3, F4 electrodes. And we stimulate for 2 milliamp and generate this model. This is current density images for these 3 people. Right off the bat, we can see that the shapes of the brain are different across them, right? And even though the general pattern of current, we have a larger amount of current near the electrodes towards the front of the brain and smaller amount further away from the electrodes towards the back of the brain, the exact pattern between these current density maps are not identical. So what does this tell us? That the brain morphology plays an important role in terms of dictating where the current goes in the brain. And then there's the need for individualizing our head models to make a more accurate prediction of tDCS. And then perhaps we can use these computational models to predict brain-based changes, such as relationship between current density and functional connectivity. So the aims for the paper is to then generate this current density maps and investigate the relationship between current density within ROIs that were used to compute connectivity and of course correlate with observed functional connectivity changes. All right, so for methods, we have 15 healthy older adults and mean age is about 71 years old. This is a crossover design, study design, meaning everyone is receiving active and sham stimulation. And the average washout period, which is the period between we delivered active and sham stimulation, is about 8.5 days. And this is an acute in-scanner tDCS. That means that tDCS was performed inside the MR scanner. Therefore, we'd be able to see the electrode in their MR images. Current density or JMAPs were processed similar to how the bold images were processed for the connectivity analysis. And the region of interest here is using the same ROIs that were used in the connectivity analysis, which is the spherical ROIs in the left DLPFC and the left VLPFC. Okay, so just a brief overview of modeling pipeline. We have the first step is segmentation, where we divide or segment each head volume into different tissue types. The reason we do this because different tissue types will conduct electricity differently, right? And on the left side, we have the T1 weighted image from our participants. And again, we can see that the electrodes is visible on their T1. So we can directly segment the electrodes and add it to with the rest of the segmented tissues in our model. In this case, 11 tissue types, which is white matter, gray matter, CSF, blood vessel, air, cancellous and cortical bone, muscle, fat, skin, and eyes. So the inside of the eyes, which is the aqueous vitreous, is actually modeled as CSF because they are fluid. So this image is showing you the variation of electrodes that were directly segmented from the T1 or MR images. And we can see here that even though the placement is at F3, F4, there's some variation across these 15 people, right? So once we segment our model, now the next step is volume meshing, where we divide each volume into a finite number of elements. So if some of you are wondering why this is called finite element methods, so this is why. And the reason we do this so that we can compute and solve voltage in this case in individual nodes connecting each elements, then we can compute local solution and eventually assemble for global solution. So we need to set up our models by assigning conductivity values that is sourced from the literature. We also need to set up the boundary condition to make sure that there's no current leakage anywhere on the scalp other than at the interface between electrode and the scalp, because that's where we remove and inject current. And then we can solve voltage, eventually solving for electric field and current density. Okay, so this is what the electric field distribution looks like in our 15 participants. And again, here, the general pattern where the large sum of current and smaller amount of current across 15 people is generally similar, right? But if we take any pair of these 15 people, for example, person number 7 and 9, we see that even though they're kind of similar, but they are not exact replica. What about current density distribution? So the top left image here showing the bold image. And we can see that the bold images kind of have blurry in nature because of how the processing pipeline is. And we process out our current density similar to how the bold images were processed. So therefore, we see the same kind of blurred effect here. And the two circle here just to annotate the two ROIs. So the black is the left DLPFC, and then the red is the left VLPFC. So what are the relationship between computed current density and connectivity? So this is for computed current density in the left DLPFC ROIs. And we can see that there is a positive correlation between computed maximum and median current density values in the left DLPFC ROIs compared to the connectivity between left DLPFC and left VLPFC. Only for active stimulation. We did not see any correlation for the sham stimulation. So the difference between active and sham stimulation, in active, we stim for 30 seconds ramp up and then stim for 12 minutes and then ramp back down for 30 seconds. But in sham stimulation, we only do the ramping up for 30 seconds and then ramp back down for 30 seconds. What about computed current density in the left VLPFC? So we did not see any correlation between current density in this ROI compared to the connectivity between left DLPFC and left VLPFC for both active and sham stimulation. So what does this all tell us then? That the current density in the left DLPFC correlated with connectivity changes between left DLPFC and left VLPFC only in active stimulation, and that the large amount of current dose within the left DLPFC ROI may be important in eliciting functional and connectivity changes between the left DLPFC and the left VLPFC. So hopefully we see that this theme of the importance that individual anatomy remain crucial in predicting brain-based changes induced by tDCS. So if we were generate this current density models from a single template head models, we wouldn't see a variation in current density to correlate it with beta values or connectivity values, right? So we need to ensure that we take into account the individual anatomy that it's giving this characteristic of current density. I'd like to acknowledge my funding sources and the lab and the center I'm in. Thank you for tuning in. That's all I have.
Thank you so much.
Can I jump in with a question? Is that,
Yeah.
Yeah, go ahead.
I was really interested, also in the previous talk, Evans sort of showed how small population size lead to variability,
Right.
which leads to the question of reproducibility. I'm trying to understand in an elderly population, and if you played the same game, is it more of an issue now, that we're not normalizing,
That is a great question. And so in older adult population, the main challenge is brain atrophy, right? So the pruning of the gyri, especially in the gray matter area, and the degree of brain atrophy is actually not necessarily depending on age. So for example, if you take like a sample from 60 to 95 years old, the 95 years old does not necessarily have larger degree of atrophy than somebody that's 75 years old. So I think it would all depends on their degree of atrophy regardless of the age within a sample. So let's say if we have 15 people, but the degree of atrophy is similar compared to 15 people who have a larger variation of atrophy, then we'll see more variation in the latter. Does that make sense? So yeah, it's a little bit tricky with the older adults population.
Yeah, someone from the audience has a question of,
Yeah.
it is interesting that you smooth electric field with 8mm kernel. Have you checked your result, your correlation result without smoothing?
Yeah, so the challenge with that was a great question. Thank you for whoever asking the question. So the challenge with why we smooth the current density is because we're using the same ROI. And if the ROI is at the edge of the gray matter, again, we're dealing with older adults population also. So it wouldn't cover the same region as if it were for the bold image. So that would be, instead of all gray matter, for example, it would be some of them is CSF, right? And if it's taking CSF within that ROIs, that would spike the current value to be higher because CSF is higher in conductivity than the gray matter tissue. So the current density would also shoot up. But that's a great question. And we did not see, we did the analysis without smoothing and we did not see any correlation.
Perfect. Okay, so our next speaker would be Dr. Kevin Caulfield. Kevin, for the interest of time, just go ahead.
Yep, sounds great. Thank you so much. Great. So sharing my screen now. So yeah, thank you so much for the introduction and for the opportunity to speak here. I'll say that I have the luxury of going third, so I don't need to go as much into depth about some of these background topics. But to start, I just wanted to list some pros and cons of tDCS. So as we all know, it's a really inexpensive form of brain stimulation. It's safe with no seizures ever reported, easy to use, which means that you can teach people how to use it and maybe they can take it home and use this in rural or underserved populations, or maybe this is a great stopgap in the COVID-19 era. However, as we've already heard, there are some cons of tDCS. So there have been variable effects between individuals and between studies, and unique to tDCS in comparison to other forms of brain stimulation, there's no widely used method of individually dosing the stimulation. And so typically there's kind of a one size fits all, either 1 milliamp or 2 milliamps supplied across individuals without respect to head size or MRI scans or anything like that. And to go a little bit more into this idea, this is just a chart of the current in milliamps on the y-axis and an estimation of it for TMS, which of course is electromagnetic stimulation as opposed to just purely electrical stimulation over time. And so for all these different forms of FDA-approved brain stimulation treatments, such as ECT, we have individually dosed stimulation parameters, such as based on the seizure threshold for ECT, tremor suppression for DBS, of course, motor threshold for TMS, vocal changes or sensation for VNS. But when we get to tDCS and tACS, there's no widely adopted method of individualizing the dosing. So I'll focus on kind of 3 studies here that all play on the same idea. And with these 3 studies, I hope to address 3 questions. So first, is there a method of individualizing tDCS dose using e-field modeling? Number 2, is there a proxy that we can use? So tDCS being this potentially a widely implemented method. So can we get by without doing MRI scanning or e-field modeling and individualized dosing in another way based on e-field modeling? And then lastly, does the cortical e-field impact behavioral outcome? So not to belabor this point, since previous 2 talks explain this so well, but this is just a general e-field modeling pipeline. So first getting an anatomical MRI scan, segmenting the head into its different parts, then meshing these together, and then assigning each of these different tissues a different conductivity value for the modeling. And then you can do an ROI analysis. So I typically do a 10mm radius spherical ROI underneath the electrode using a gray matter mask as well. So the first study I'll go into, and Aprinda actually nicely touched on some of the aspects of the study, but the parent study is this Neeson et al. Paper in 2019 in Frontiers in Neuroscience, and this was done in collaboration with Dr. Adam Woods and Dr. Indahalastari. And so here they recruited 28 healthy aging adults, and this is the study design. So doing a baseline MBAC task, then 10 sessions of active or sham tDCS, and then having a post-intervention MBAC task as well. And here are the electrode placements. So bilateral F3, F4. And yep, so each person received an anatomical MRI scan, and this allowed us to do e-field modeling on each person's MRI scan on each of the 28 individuals. So the first thing we wanted to do is visualize what this looks like. So when we apply the same 2 milliamp tDCS dose for each person, what does it look like? And so we do see that there's a lot of variability here, that from that same 2 milliamp dose, some people are receiving higher or lower electric fields. And so we were wondering if there's a way to control for that. And we've already heard a lot on this topic, but this is the method that we use. So we ran an initial electric field model for each person. So we placed the electrodes, ran the electric field model, and then did an ROI analysis to extract the average E field in that spherical ROI for each person underneath the center of the electrode at the intended cortical target. And for example, if for this person it was a 0.255 volt per meter electric field, then what we did was we created these proportions of the 2 milliamp dose input over the electric field output for each individual person. And then we created this proportion to the individualized dose over the group average electric field. And I'll point out that you can do this for any electric field. Here we just so happen to do it for the group average electric field. And then by cross multiplying, you can solve for the individualized dose. So then when you put that back into the modeling the second time, you can produce the group average electric field for each person. So going back to this visual of what it looks like for each of these 28 older adults. So here's the variability that we saw from the 2 milliamp dose for each person. And then when we individualize the tDCS dose, I hope that we can appreciate that it does look more consistent between individuals. And to further drive that point home, I pulled out the person with the lowest initial electric field from 2 milliamps, person with the median most electric field from 2 milliamps, and then the highest electric field from 2 milliamps. And so what we see is when we individualize the dose, we would have to put in more, a higher dose for the person with the lowest initial electric field, but we can get that group average, which in this case was 0.221 volts per meter. For the person with the median most electric field, it doesn't change much. So it's about a 2 milliamp dose still for that group average electric field. And then for the person with the highest initial electric field, you can actually get by doing a lower dose than 2 milliamps to produce that group average electric field. And when we look at this quantitatively, so here on the y-axis is the electric field in volts per meter. There is a lot of variability when you have the 2 milliamp produced electric field for each person, and we can produce the exact same group average electric field of 0.221 volts per meter but we can reduce the standard deviation by 2 orders of magnitude. And when we use the Levene's test here to look at the variability, this was statistically significantly lower variability from individualizing the dose. So as an interim summary, so here are 3 questions again. So first, is there a method of individualizing tDCS dose using E-field modeling? And it looks like maybe we do have a method of doing that. So next, we wanted to see if there's a proxy measure for individualizing the tDCS dose without using MRI scanning or E-field modeling. And so this got us thinking very historically, actually. So we thought about using transcranial electrical stimulation, or TES. And what I mean by that is not TES as a conglomerate term for, tDCS, tRNS, tACS, but rather single pulses of TES to elicit actual neurons firing and maybe observable MEPs in the contralateral hand. And so this is not a new form of stimulation. In fact, it predates TMS. So this was developed by Merton and Morin in 1980 in Queen Square, published their first paper in Nature. And these authors observed that one of the best ways of determining cortical function is to stimulate it electrically, but that this was only available in a neurosurgical setting in the past. And so they developed a way to transcranially deliver single pulses of TES to elicit contralateral hand movements, which is what we're seeing on the right. However, the biggest drawback of TES single pulse is that it can be painful. So that's why when TMS kind of came around in 1985, that became a more predominant form of stimulation. However, in this case, thinking about how we can use single pulses of something, whether it's TES or TMS, to dose tDCS, we thought that TES might be good because it's electrical stimulation. So that's a more similar form of stimulation to tDCS than TMS being electromagnetic stimulation. And so the study overview here is that we recruited 29 healthy adults, and in the 2-visit study, so in visit 1, they had a TMS motor threshold and then TES motor threshold with the electrodes placed on the TMS motor hotspot, as well as extracephalically on the left deltoid. And we measured MEPs from the contralateral right hand. And then in visit 2, each person had an anatomical MRI scan, which allowed us to do the E-field modeling. So here's what the setup looked like. Again, an anodo tab electrode placed over the motor hotspot, cathode or ground plate electrode over the deltoid with tab electrodes to measure MEPs in the contralateral hand. And the stimulation for single pulses of TES was delivered using a digitimer with these settings. And we were able to get a motor threshold approximation for each person using an adaptive PES procedure, so 5 pulses per person. And I'll say that in the paper, we have pain ratings, but this was less painful than high frequency RTMS, and no one dropped out or anything. So we were able to do this in a way that was relatively painless. And so for the E-field modeling, we placed the electrodes in the same locations as the TES electrodes were in, with the exception that instead of the left deltoid, since we didn't have that part of the scan, we placed it as low as possible, kind of in the neck area. Okay, so what did we see? So here on the y-axis is the reverse calculation tDCS dose. And we did this for 1 volt per meter electric field because we wanted to remain agnostic as to what electric field you might want to dose at. And then here on the x-axis is the TES motor threshold for each person. So we correlated these values together and came up with an R-squared value of 0.45, which was statistically significant. And what we proposed is that maybe you can use the regression formula, so y equals mx plus b in this linear regression, determine someone's TES motor threshold without the E-field modeling. So to use this previous E-field modeling that we have. And then, so for example, if someone had a 60 milliamp TES motor threshold, to then calculate what their individualized dose would be based on these prior data. So for this person, it would be about a 6 milliamp dose for that 1 volt per meter E-field. So that's really high. But again, going back to the idea that you can use this for whatever threshold you want. So it's linearly scalable. So if instead of 1 volt per meter, you wanted a 0.5 volt per meter E-field, you would just divide this by 2. So it'd be about a 3 milliamp dose for that person. And I just wanted to point out this new brain stimulation paper where the Antonenko et al. Published it recently and correlated head circumference with the E-field intensity, and actually found that participants with a bigger head size actually produced on average a lower electric field. And so this might be even another method of even more simply taking into account some measurements to determine the E field intensity to dose at. So again, going back to the interim summary, it looks like we do have a proxy measure of individualizing the tDCS dose without MRI scanning or E field modeling. And then lastly, I just wanted to touch briefly on whether we think this matters. So if we do have a method of individualizing the tDCS dose, is this going to impact the behavioral outcome? So going back to this collaboration with Dr. Adam Woods and Dr. Indahalastari, and the parent study with Nisam et al. In 2019, published in Frontiers in Neuroscience. So now we're going to focus on the behavioral outcome of active versus sham tDCS. And these are the results of the initial paper. So in black here is the active 2 milliamp stimulation condition. And unsurprisingly, these participants had a statistically significant improvement behaviorally in working memory accuracy from pre to post stimulation. So their improvement was about 11%, whereas the sham stimulation participants did not experience this. But what we were really interested in is breaking this down into higher electric field from 2 milliamp and lower electric field from 2 milliamp conditions. So the question here being, are people who are just so happen to be receiving a higher E field from 2 milliamps based on their individual anatomy, are they going to have more of a behavioral improvement? So we split this into two conditions. The 7 participants receiving a higher E field from 2 milliamps, the 7 participants receiving a lower E field from 2 milliamps. And what we saw is in red here, that's the high electric field from 2 milliamps condition, that these participants improved about 15% in working memory accuracy from pre to post stimulation. For those who received a low electric field, so still active stimulation, but a lower electric field from 2 milliamps, they still had an improvement, but it wasn't statistically significant of about 7%. And then the sham stimulation participants didn't seem to improve at all. So as the overall summary, so we had 3 questions, and it looks like we do have a method of individualizing tDCS dose using E field modeling. So we call that reverse calculation modeling. We do have a proxy measure for individualizing the dose, maybe TES motor threshold or the head circumference size. And then it looks like in a small sample, and this would need to be replicated and done in other populations, but it seems like the cortical E field might impact the behavioral outcome. So just to leave everyone with a couple of future directions, it seems like maybe we can think about prospectively individualizing the tDCS dose and seeing if this affects the behavioral outcome. And then another future question is there an optimal E field threshold? And maybe there's an E field threshold that we can use for individualized tDCS dosing moving forward. So with that, thank you to everyone who helped on these projects. And yeah, that's it.
Thank you so much, Kevin. It was really nice. And we are right at the time. I just wanted to have a question. Probably like you and everyone else can talk about it or answer the question. I hope by now everyone is on the same page that there is variability, and a portion of that variability is because of the anatomy. I wanted to say, what are your thoughts on post hoc correction for the variability on electric field intensity and distribution compared to like doing it beforehand, like individualizing the dose and applying to different people? Would that make any difference? And I mean,
yeah, I'll take a stab at that first. But yeah, I think that's, of course, the big question. So we have these really advanced methods now that are really exciting that we've used to retrospectively look at data and look at how the E field is variable between individuals and how it retrospectively might have impacted the outcome. But of course, I'm most excited about applying this forward and seeing if it can actually make a difference in terms of maybe more consistent effects from tDCS. Or maybe slightly bigger behavioral effects across studies and between individuals as well. So I think this is a really exciting area for me.
I don't know the answer. I think that's such a good question because is it too late after the fact? You know what I mean? Yeah. You know what I mean? It's an interesting point, right? We can go back, but is there some reason to do it ahead of time?
I mean, we know the responses in brain are nonlinear, so it's not probably in post hoc you won't be able to like linearly take everything out and say the responses are linear. So we should be okay, but not in all the cases. So yeah, I wanted to hear everyone's idea on that. And is there,
I think
I'm concerned about it. Yeah.
Yeah, I mean, I think what's just so useful now is to really lift the lid on what we're doing. I mean, we are just scratching the surface at what's going on. And whilst we are doing it post hoc at the moment, we are still getting a much greater understanding of what is happening when we put 2 electrodes on the scalp and run current through the brain. But we've barely scratched the surface at the same time. I mean, we're even just touching upon the complexities that there are. I mean, I mentioned 3 things that are just purely about current in the brain without even considering the state that that brain is in at the time you're stimulating it, whether that is during a task, not during a task, during different times in people's lives. So aging, that's a huge factor that will disrupt. We haven't even gone into pathology, which is another component which adds a whole new mix of issues. So what happens when we apply all the assumptions we gain here to a stroke population or to ALS or anything else where we expect differences, whether that is structural or just basic functional differences. So it also, I guess, twofold. How complex are we going to get at the end of the day? For the reasons I think Kevin really is kind of touching upon, and we have to be mindful of. This is supposed to be a cheap and easy technique. It's supposed to be accessible. And when we get ever more complicated, it becomes ever more inaccessible. So I think we need to learn as much as we can, but then be mindful about how we can take the norms that we get from this data and simplify. Can we backtrack and simplify our methodology to enable this to still be accessible?
Perfect, thank you. Okay, there is Jake Todd, I guess, is asking question from Kevin. Do you think some participants require a greater intensity than is tolerable, more than 4 milliampere? And if so, is there any way around this, such as interference pattern of tDCS?
Yeah, no, that's a great question. I was actually just answering it in the chat, but thank you for asking it. So I think we need to kind of tread lightly about higher intensities, since there does seem to be some evidence of nonlinear effects of tDCS, at least over the motor system and above a certain intensity. So some researchers have gone up to 4 milliamps, but I think to date have not tested the behavioral effects of it, as far as I know. But I do think that if someone desired to go higher, that tDCS would be an interesting and a good idea in terms of tolerability. But it's unclear whether that would be a good idea or not, or have a good behavioral outcome, I guess.
There's another question in the chat, which I guess all of you can answer, or like whoever that thinks it's relevant. How will we do group level comparison when doses are different? Suppose we are giving 2 doses in old and age group. How can we conclude the effect is due to age or difference in doses applied?
This is a great question, and I feel like this is the question of the century. So in terms of comparing, I guess age means young adults, I'm assuming, compared to old. I guess from what we do with computation modeling, this models is based on the ground truth, which is the MR images, right? So the information is limited to that, which is the anatomical feature that we see in the MR images. But of course, there's maybe other age-related effects that's beyond that we cannot see beyond this MR images. So we so far know that brain atrophy, which is again degrading of brain tissues that have this causing this pruning effect of the brain tissue, occur usually in older adults compared to young adult. Usually young adults have a nice fluffy brain, and we're talking about only in the healthy population, right? As this population, we might have a different feature. So based on the assumption that all the degree of atrophy related to age effect, we can maybe perhaps conclude that the different doses that applies is related to age effects, especially the brain atrophy, and maybe other age-related effect that we can see from the MR images. But I can't personally, I don't know, but maybe everybody else have a idea on this, on saying yes, this is due to age effects, and no, this isn't, because we can't say something that we cannot see, right? So that's my take on that.
I guess, I mean, touching upon this idea, as I understand the question of, if two doses are different, how can you compare those two groups? Applying a fixed dose, now again, using the term dose, if we're talking about stimulator output as dose versus what's actually input, what's in the brain as dose. A fixed dose on the stimulator output of 1 milliamp does not equal a fixed dose inside the brain. So already we're making comparisons across two groups that are fundamentally different. Because for the reasons I described, again, with that bootstrapping data, we could have two entirely different populations. The electric field that is actually in the brain, whilst we've applied the same intensity, is different. So we're already comparing two different groups and wondering why maybe one shows an effect and one doesn't. So if we were to alter the dose in two groups, we're just talking about shifting variability. So dose, instead of being variable in the brain, is now variable outside. And therefore, you might argue that that's more comparable than what we've been doing to date, I guess.
Great point. Thank you. There is another question for you, and I promise that is the last one. I guess someone asked this question, the name doesn't appear here. Hi, Caryas, great work. Is it directionality analysis for conventional 2 milliampere, 25 centimeter square montage or high definition?
Sorry, yes. So this was the direction data. This was with conventional bipolar montage, and we used the same electrode sizes that we have in the lab. So they're about the size of, I was about to say a 2 pp, so that's going to fall on deaf ears, but it's I think about 17 millimeter radius, I think, about the standard size for electrodes. So yeah, the directional data we have looked at was for a bipolar conventional electrode montage. We haven't looked at high def data as yet.
Great, thank you so much. I guess we are 10 minutes late, and sorry everyone. And I need to thank all the speakers. It was amazing discussion, and I hope we keep it going. And the next journal club will be in 2 weeks. And for now, I can just say the theme will be TMS EEG, but stay tuned. Will be posted on our Twitter account for Brain Stimulation Journal. And that's it. Have a nice day, everyone, day and night, wherever you are, and bye.
Thank you very much. Have a good day.
Thank you.